Hey there. Got all the buttons clicked. Great to be here. And thanks to you all for being here. This is actually, I'm coming to you live because we wanted to shake things up a little bit. So you can still ask questions along the way. And Randy, the track host, is here. He'll keep an eye on them. And whenever I take a breath, he can shoot the hardest ones at me. So so we're live the whole time. Send those questions and ask them whenever it fits naturally in the flow. I'm really live. I'm really here in real time. Okay, so I'm Mats Torgersen. I am the current lead designer of C#. I've been that for a good half decade now and worked on the language for about 15 years, during which, and you know, it's just a bit older than that, about 2 decades old, and during that, it's gone through a phenomenal journey of transformation, and sort of started out as a very classic, very turn of the century object-oriented language, mainstream object-oriented language, and has evolved a lot. And many of the things that happened over time were inspired / borrowed / stolen from the functional world. So there's been a lot of crossover there. And I'm going to sort of, just to put some structure on it, there are many things that we can talk about here. But just to put a little bit of structure, I'll start in the past, you know, talk about the kinds of functional stuff we were getting into C# around the time when I first joined 15 years ago, and throughout that period, where it was very much about trying to enhance the, staying within the object-oriented paradigm, but trying to enhance it in various ways, in particular around control flow and those kinds of things. Then we went into a phase that we're still in, where the focus, which was really sort of triggered by the cloud, really, and devices, and the fact that much more than in the distant past that many of you probably don't remember, data is something that is shared between many different applications, and that's concurrently, and that's a scenario where, in some sense, history is on the side of functional programming. And so this is a point in time where we had to not just enhance object-oriented programming, but kind of provide an alternative within the C# language to supplement the object-oriented programming with making a more functional paradigm easier within the language. And then finally, we can talk a little bit about the future and some of the thoughts we have in different directions of being inspired by functional programming, including how to through the type system, how to really get rid of some of the strong dependencies that are a bit of a tax on software development processes in object-oriented programming today. So that's sort of the overall structure of it. And I'm going to spend most of this talk, like the 2 first bullets of these 3, I'm going to spend in Visual Studio, which some of you may have heard of. It's the world's first and foremost IDE. I'm sure many of you will agree with, and it's coming from Microsoft. It has excellent support for C#. So I am going to go right in there, and we're going to simply take a little journey through the first 3 versions of C# and all the functional stuff that happened there. So this is a C# 1.0 program, pretty much. I'm cheating a little bit, attempting to abstract over some functionality in to have using first-class functions. And actually, the very first version of C#, unlike many object-oriented programming languages, actually supported first-class functions from the get-go. So you have function types. You can declare. You have to declare them. They're nominal, just like declaring a class or an interface or a struct. You have to declare a delegate, as we call them. They're sort of function types. They're really crappy in many ways, but I'm not going to go into that. But they get the job done. You declare the predicate type here as something that takes an int and returns a bool. And then I can write a method that takes a predicate using that type. And when I call the method, I have to pass it. There are no function literals yet. So I have to pass it a named method, right? So I can pass it the method greater than 5 here, which fits the type sort of structurally. And therefore, can be converted to a delegate object, which is a function, a first-class function, passed to the filter and applied there. And you can see the application of it here, the little calling of P here. You can call that as a first-class function. So that's already in C# from the get-go, which is a little bit of a leg up on some of the other languages. But obviously, it's fairly clunky and so on. It's also, from a type perspective, it's not like super elegant, and that's something that it shares with many most object-oriented languages at the time. That the programming world sort of has these two different kinds of polymorphism, two different ways that you can write code that applies to multiple different types at a time. And the functional camp has gone with parametric polymorphism, where you are parameterized over types. Your code is parameterized over types and can be applied to different types. And object-oriented programming had gone with subtype polymorphism, where you have hierarchies of different classes, and they can all pose as the base type and sort of be mixed together, like in collections and so on like that. And both have strengths and weaknesses. And around the turn of the century here, we were all engaged in trying to figure out how to get parametric polymorphism into object-oriented programming languages, and to help with things like, you know, I have a collection here that is untyped, and I have to cast. I put ints into it, but I can't say that, so I have to cast them as they come out again, and so on. The whole thing is specific to ints. There's no abstraction over types. So first thing we do, C#2, is okay. We need parametric polymorphism. We add generics. And so now I can make my types generic, so I can make my predicate type generic here and have it apply to all kinds of values, not just ints. That's very nice. And of course, I need to then say that what I take here in my filter method is a predicate of int. But I can also make methods generic. So, and many of you, if you don't know C#, you also know this from Java. It should not be a surprise. The support for generics in C# is a different, mainly in that it is worked all the way into the runtime. It's not erased by the compiler, so it has it sort of runs deeper, if you will, and it's more complete. And so I can make my filter method generic as well, saying, oh, I can take any kind of predicate and any kind of array and return that same kind of array, and now I should be able to, if I can just replace all the ints with t's here, I should be able to apply the filter to anything. I should not replace that one. The filter to anything that is a you know, as long as the t's match up in the signature, so to speak. And here you can see that my call to filter doesn't actually need to pass int explicitly as a type argument. That can be inferred implicitly. So there's a little bit of type inference that's also creeping into C# at this point. Okay, so that's generics. But with generics arrives the opportunity to have better libraries, right? That's a big thing when you add generics. You can add generic libraries. Let's forget about these old clunky collections. Let's have some generic ones. And now we can chuck this array list on the garbage heap, and we can use list of t instead. New generic list. And of course, that is all very nice. Now I don't have to cast things when I take them out, because they're already known to be, you know, all these benefits. But what's more, list of t can actually have better methods on it because it knows its type. So we could actually just return calling the to array on this accumulator method that we have, and we don't even have to do our own manual building up of the result here. There's a method for that, right? So generics really help with the abstraction here. All by taking this functional programming language kind of polymorphism into C# as well. So that's probably a good place to ask if there are any questions so far. Randy is here, track host.
Not any questions so far, Matt.
Okay, this should be sort of repetition for people who went through this in real time. And the rest of you who just grew up much later than us, you'll be like, what? That's like, that's completely basic. But it's, you know, this is how it came into C# and to many object-oriented programming languages of that age. And it sort of was just became the new standard for what should obviously be in any modern language. Now, we can actually do a little better here. There's now also other, array used to be the only generic type. Now we can have other collection types. So for instance, we can have one that's called IEnumerable of t, which abstracts over essentially anything that can be iterated over. So we can take IEnumerable of t, and we can return IEnumerable of t. And I'm getting sick of writing types all the time, so I can use, I'll cheat and use the C#3 feature here and just use type inference on local variables here. But IEnumerables can be for each over just like arrays and everything else. Now, when I do that, I can now write my method as a generator, which is another thing that came out of the functional world, where I am lazily producing the results of this filter as you ask for them. So instead of having this accumulation into a temporary collection and returning that, I can simply say yield return, because this is an old language. We have to have some syntax there. Yield return the value, and then I don't need the temporary collection, and I don't need the return. I'm simply now writing a generator that whenever the for each here asks for the next value, the IEnumerable will go say, oh, let me run the next bit of code that produces that. So again, another functional thing that makes it into C#2. The last thing, though, is the first attempt at having function literals, or anonymous functions, if you will. So instead of having to have a named method for everything that we want to pass as a function, we can now say, the syntax isn't like beautiful, but this is the first like run at a syntax for anonymous functions. And we can get rid of that declared method there. So far, so good. Now comes C#3, and we want to we want to start addressing scenarios like interoperating with databases. So we have what we call language integrated query is the big new thing here. And in order to do that, we need to do better on the functional front. So first of all, let's take this clunky syntax and let's give that a do-over. Let's have lambda expressions in C# instead. You can write it like this, which isn't much better, but lambda expressions can optionally, have expression bodies. So that gets a little better. And also, we get more type inference, so you don't actually have to say the parameter types of a lambda expression, as long as they're passed to something that will tell them the type. So more type inference here. Because we're calling filter with an array of ints, then t will be inferred to be int, then this is inferred to be a predicate of int, and therefore int is pushed back down into the lambda, and its body is type checked in the context of that. So more and more type inference there. We also realize that we're going to be using first-class functions a lot. So this whole declaring your own delegates, like that really sucks. Other functional languages, they have typically structural function types, and we should get at least closer to that. But we can just add a library of generic delegates to C# itself. So we now have func of t, bool, and that's a delegate type that's pre-declared, and we have them like up to a certain number of parameters. So which grows for every release, right? Because we want to try to capture bigger and bigger functions. So we can get rid of that as well. And now we're down to something that is fairly neat. You saw the var here. We can put var in many places, more and more type inference. Who needs to see the types all the time? But then, one thing that when you start using something like filter here, you might want to apply more than one filter, and now it gets really annoying because I have to sort of want to apply a filter to this, then I get this sort of nesting going on. So let's say I want to get all the things that have, where 3, that can be divided by 3. that just looks really ugly. That kind of becomes a lump of code. And so what a functional language would do here is that it would have a pipeline operator. So it would say, hey, the first parameter there, why can't we can pipe that into a function call with some syntax. C# can't do this, so I'm just sort of going to wing it here. And I could even take the original array, and I could pipe that into the first filter call there, something like this. So this is what a functional language would do. And we don't put that in C#, but what we do instead is we say, okay, you can declare a static method like this. You can declare it as an extension method, and that means that it can be called on its first parameter as if it was an instance method on it. And so now I can say array.filter, and I can say that dot filter, and you get that fluent flow that you would get in a functional language as well. So yet another inspiration there. So extension methods have really proved their worth in C#. But of course, querying is a general thing. So we add a library called link for language integrated query, where you don't even have to write your own filter method. You can just use the where method from there, and it looks exactly the same way as the filter I just used. So we can get rid of that as well, and we're doing some querying here. Now, one thing that, I mean, this is really beautiful. You can add other query methods. You could have, like, instead of here, you could have like a select method where we transform the result. And so let's say we also add support for little anonymous record-like thing. So I could output an anonymous object of x and the and x squared or whatever, y equals x squared, some silly thing, and you can sort of put together what looks like more and more like a SQL query. But you really like some nice syntax, just like SQL. So we could say from x in array, where x less than 5, select. You can now write this as a syntactic sugar for the same thing, right? For there we go. For stringing together these calls and lambdas. And this is, again, a functional construct. This is a list comprehension or query comprehension. It's monadic, so it's a monad. C# has monads in this particular case, and it does the job. So that's sort of like the classic phase. We also have, I don't want to show it here, but we also add the ability to actually quote lambda expressions, so that when you pass them, instead of passing them to a delegate type, you pass them to another kind of type called expression of t. You get, instead of getting a lambda function you can execute, you actually get a syntax tree of the lambda at runtime. So code quotations, Lisp style, comes in at this point, and that's how we built our ORM support, the object relational mapping. When you write a query like this, it gets translated into a tree that can then be passed to a SQL translator, turn it into SQL, pass it to a SQL database, and run the query like that. So that was our first functional boost. Want to hear if there are any questions so far?
So there was a question about if there's any aspect of the C# syntax you would retire. And I recognize you're only at C#3 at this point, but I thought that was a cool question.
Yeah, I mean, certainly that first shot at function literals, the anonymous methods, was like a clunky mistake, and we overwrote it immediately in C#3. Of course, we can't take it out, but coming up with a better lambda, more flexible lambda syntax, that's an obvious one. I also think these delegates, I'm not showing the underbelly of the delegate types, the function types, but the way we designed them, they really weren't designed in C#1 for functional programming. They were designed for programming with events, like supporting subject observer style kind of eventing. So they have all kinds of, they're actually not just, they can contain more than one function. They can contain like a list of functions, and if you execute them, all of those functions will get called, and only the last one you'll get its result, and so on. It's really hideous. So that I would just like have done. I would have a do-over on that whole thing if I could. I hope that answers the question. That's some of my common regrets.
We may get to later. How does the current and envisioned future state of C# support for functional programming stack up against, for example, Scala, which we know is a purely functional or like more functional language?
Right. So one thing, I love Scala, at least in some details I don't like, but I love Scala in its philosophy, which is to produce a genuinely, not so much a multi-paradigm language, but a unified paradigm language where everything is carefully worked together. And as we add functional things to C#, we try to do it in the same way where they fit well with what's already there, rather than being sort of like a separate part of the language. So I really adore that as a philosophy. I don't think we'll get to where C# is a complete balance between functional and object-oriented. We're always object first. So, and we're never going to compete with like a functional first language like F#, for instance. Like there's so many things from functional programming, so many idioms, such an amount of type inference that we could never get there from here. So it's sort of in between there. But we take these functional things in not because we want to be multi-paradigm, but because there are scenarios where it's really useful. And that's sort of is there another question? Because otherwise that's a great segue to the next section.
Halfway point to give you a time check.
Yep, good. Perfect. So the next wave really is this cloud-driven wave where object-oriented programming focuses a lot on encapsulating functionality and data together. And that's great for some scenarios. It really had a golden era, and it's still good for many things. But when your data is in the cloud and is being shared across many different application areas being used in different ways, then packaging the functionality in the data just doesn't make sense anymore, right? There, you really want to have the functions on the outside, not on the inside, which means the core data needs to be public in the data type. It often needs to be immutable depending on how you architect, and you need to be able to do the things that you do by having virtual methods in an object-oriented program. Like you have shape-dependent behavior by overriding virtual methods in a hierarchy. Those things, that kind of shape dependency, you need to be able to express from the outside, right? You need to write a function that takes some object in. The object doesn't know about the function, but the function itself does different things depending on the type of the object. And that's what pattern matching is for. So in C#, fast forward to C#7, we get pattern matching into C#. And we start laser focusing on that scenario only. So if you have some sort of, let's say, void M that takes an object O, now you've always been able to say, what's it complain? Oh, it has to be static. Sorry about that. You've always been able to say in C# if O is string, for instance, and get a Boolean result back. But now when you want to do something about it, you can't. You've lost it as a string. You checked that it was a string, and then you lost it. So you'll say something like console or write line of, yeah, it was a string. What if you could just, give that string a name while you're at it? And now you can say string. We can output the string as well. So like this, and then interpolate a string. This now is an example of a pattern, right? And we just allow patterns initially. We just allow them in the places where they inside of already existing control structures in C#. So there's the is expression gets enhanced to not just check against types, but to check against various patterns. Switch statement as well. I can say switch and switch of O. And instead of just comparing against constants in the cases, a switch syntax is just hideous in C# as well as all the other C-based languages. I can say case, and instead of just using constants here, I can say case string S, and then go do my thing. Of course, it's classic. It's classic switch stuff where you have to put a break in order to close things out. But so now I can use that alongside with, and we sort of retcon constants as well, like constant values, they're also a kind of pattern. So I can also say is null or things like that. So now patterns have a place in the language, and they're only these two kinds of patterns pretty much to begin with. But then since then we've been expanding on what kinds of patterns do we have in C# and where can they be used, so that we get more towards the expressiveness of C#. And I want to show you an example of that, where we've since what I showed you, we've evolved C# to now have expression bodies in ordinary methods as well. So this is an expression bodied method that takes in some object. And again, this is trying to apply functionality from the outside of the object model by saying, hey, okay, which kind of thing is this? Oh, if it's a car, then we do one thing. If it's a taxi, well, then the pattern is more fancy. It will apply what we call a property pattern to the taxi and look at its fares property and apply. Now it applies a constant pattern to it. Say, oh, there's 0 people here, so they have to pay this much to go over the bridge, which this is all for, right? Or we have deconstruction in the language now. Bus has a deconstructor, so we can apply a positional pattern, applying patterns recursively again to the parts of the bus, if you will, the wheels on the bus. Not that, but other things. We have, in this nested switch here, we have relational patterns now coming into C#9. We have logical patterns to and or not to combine other patterns and so on. So we get this whole patterns have gone off as a thing of its own. And of course, this whole thing is not a switch statement, but it's a switch expression, which is much more nifty and modern and so on. So this thing has ballooned over time to be a really expressive part of C# from being not there at all a couple of versions ago. Like C#6, there was no such thing as pattern matching. So that's a big concession to, you need this style of programming to make up for the fact that you can't wrap the functionality up with your object hierarchy. I think you're seeing many languages doing the same kind of thing, all driven by the need to work on outside data. So speaking of outside data, one of the things you often want to do is treat that outside data more as a value, and often also work with it as an immutable value. Okay, so here's an example where this is me before I was married, and then I changed my last name. That's how you would classically, you'd mutate the thing, right? And we added support for classes like this in C# now to have properties that can only be mutated during initialization. So in this object initializer here, when the object is being created, I can still mutate the properties, but I can't change the last name. If I want to change the last name, I need to create a new record. Like I need to have an immutable discipline where I create a copy, I copy and modify, right? I do a non-destructive mutation. And in order to better support that, in order to support sort of like value semantics like that, you now also have records in C#, which come with a bunch of also abbreviations and stuff. I'm not going to show you, but the main thing they give you is they give you value semantics by default. So instead of like always assuming object-oriented stuff, and you have to sort of overwrite the defaults and write very long things to be immutable and value-based, they give you this by default. So instead of creating person.last name, I can now say var new person equals person with last name equals Torgersen, right? So there's non-destructive mutation supported in the language on records, and more types will come over time to support non-destructive mutation, where you can say it's like that one with everything copied over, and that's sort of merged with the object-oriented paradigm, where the new person, you can see that I'm actually creating an employee here, but I'm only storing it as a person. But the new person here will also be an employee, and they will also copy over even the things that can't be seen statically at this point in time. So that's sort of like the that's sort of like trying to fit this in with with subtype polymorphism. You really need to make sure that non-destructive mutation works well, even when you don't have the whole truth about the actual runtime type of things around at the point where you do the copying and mutation. So The other thing with records, and I think just for time that I'm not going to show, is I can just tell you, it's that they have value equality. And so they will, you compare two records, that corresponds to comparing all the members and making sure that they're equal. And we take care of generating all that code and the hash code, and also making sure that it's symmetric. So, I mean, a big difficulty is writing it's not difficult per se, but it's a maintenance nightmare to maintain a manually written equals function that is symmetric and remembers to deal with all the data and so on. So we do that for you as well in records. So that's another like step towards functional programming, if you will. This will be a good point in time to get a question or two.
Perfect. Yeah, there were several people wondering about performance concerns with immutability.
Yes. So immutability as a discipline, and this goes, pretty much regardless of the programming language features, that whether they're nifty or not. Like typically with immutability, that means allocating a lot of objects, right? In C#, sometimes you can get around that by using structs instead, but that's like, then you have higher copying costs as well, because structs are value types and they assign by copy. So if they're big, the lesser evil is to have them be reference types, to be classes. And records here as well are classes. They are objects. And we've built very big things that use an immutable discipline. The whole C# compiler, including the C# compiler is not just a compiler. It's an API that can give you every detail of every syntactic and semantic detail about a C# program. It can help you build build more C# code, and it's what's being used by the C# IDE. Here, as I'm using the IDE in front of you, it's using incremental APIs and everything. So it's a big API, and the whole data model is immutable. And so we've had to. And performance really was a problem. Allocation was a problem as we built it. And we've had to do tricks along the way to share as much as possible, to cheat, to use structs where we can, to cheat and not copy things where we can, and so on. So that's sort of like the scourge of immutable programming, if you will. And I don't know that as much we can do about it other than try to tune our garbage collectors for it. Yeah. Was another question there, Randy?
Several, but I think for interest of time, I'll give you one, which is what you're doing. When would you choose a class versus a record, and vice versa?
I think, records really are classes with extra bells and whistles. So when the defaults of classes, reference, equality, mutability, when those things are not what you need, that's when you choose a record. When you need to be value-based and potentially immutable. Typically, you don't have to be immutable. Like I can totally have a record that's mutable. C# doesn't prevent it in any way. But you just have to be careful when you have mutable reference types with value equality, because the hash code will change over time, and you stick that sucker in a hash table and you mutate it, it can never be found. So they just, there'll be dragons. But yeah, the core choice really is, I am working with data from the outside, and I'm treating it as data. I'm treating it as values. I don't care about the object. I will have object identity as a reference type, but I don't care about it. It's not the important part of the data model. You still have inheritance. You see the records inheriting from each other here. Get all that modeling. That's sort of if you wanted to have discriminated unions, like we might add some shorthands to C# later to give you something like discriminated unions from functional programming, but this gets you a fair bit of the way in that you can have these value-oriented types where you can create a hierarchy to model the fact that there's a type with multiple different shapes. So this gets you very far of the way towards discriminated union style semantics. And with that, I think I will I'll go to the last bit, which is shorter, so you shouldn't be too worried, Randy. Which is the future. Let me get this up on the screen. So one thing that a few functional languages, notably Haskell, has really nailed is that in Haskell, they have this thing called type classes that allow you to state, to express that some types abstract over some types having a certain number of functions, and then to say that a given type satisfies that type class. But when you say that, when you witness that, as they say, you can do that independently of the declaration of either the type class or the concrete type. So you kind of have a third place in the code where you put them together. And that gives an amazing amount of decoupling. That is a bit of a type coupling is a bit of a scourge of a lot of programming, including definitely object-oriented programming. Like, in order to abstract over in order for a class to implement abstractions, it has to implement an interface, for instance. And so it has to say right there that it implements the interface. It has to have pre-knowledge that it was going to be used in the context where the interface makes sense. And so it's been interesting for us to study, is there something we can learn from type classes and kind of flip them into a fully object-oriented feature set that could help us with that. So that's what I'm going to show you here in the last 2 minutes. So one thing is that this whole idea of functions on the outside, they're sort of represented in C# by static members in many object-oriented languages. And so if an interface could abstract over static members, like static properties and also operators, which are overloaded in C#, then we could say that int implements this particular thing that has a plus and a 0. And if we constrain our generic by it, then we can now write generic numeric algorithms, for instance. So that's kind of nice, talking about the functions that apply to the type rather than just the instance members. But we still have the strong coupling here between the int type, and it has to know about the imonoid and implement it. So that's the problem here. But what if you could instead say that somewhere else? Like, what if after the fact I could say, well, here's an extension that tells you, if this is in scope for you, then it tells you that int32 implements the imonoid interface, like as a sort of like a third-party declaration. In the scope of this declaration, I know that int32 actually implements this interface, even though the type and the interface didn't know about each other inherently. And I can even say, how it implements the interface in the cases where it doesn't already, like, it already has a plus operator, so that's implied. But I can say, I can explicitly specify here how the witness here can say exactly how I implement this. So that's sort of like a kind of direction that we are thinking about taking the type system that can really, I mean, it's going to be hard to do in practice, but we're working on it because it can really sort of affect software development and decoupling of components in a way that object-oriented programming kind of needs. So with that, I want to say thanks a lot. It's 9:40, and we should head over to the hallway to continue the conversation. But thank you so much. It's been a pleasure.